Okay, we'll start talking about sensitivity analysis, and before that, I need to tell you how the dual simplex method works, because that's quite handy in the context of sensitivity analysis. So here, if you think of the simplex method, if you have any basis B given to you, inducing a feasible solution in the simplex method, this defines a basic feasible solution by B inverse B. It also defines a complementary dual solution, which we call W, defined by CB B inverse. Now, the CB B inverse, if the basis B is an optimal basis, this is going to be a feasible and optimal solution to the dual problem. However, if B is not an optimal basis yet, if it is suboptimal, in that case, W will, well, it can still be defined in this way. In that case, of course, it will not be a feasible solution to the dual problem. It will violate feasibility. For that reason, it's called the complementary dual solution sometimes, or typically the more proper name is the vector of simplex multipliers, okay, in case B is not optimal. So W may or may not be dual feasible. What do I mean by feasible or not feasible? Well, for the standard form problem, minimize Cx subject to Ax equals B, x greater than or equals 0. If this is your primal problem, then in that case, the dual problem is a maximization problem, Wb subject to Wa less than or equal to C with, well, that much. No restriction on the W. So, of course, this W has not, well, you know, W here is a generic vector of variables, okay? It's a dummy vector. Here, it's defined in a particular way, so there's a difference. But what we mean by dual feasibility is the following fact. If you look at the vector of reduced costs, R, that's defined by CBB inverse, and if you put W for CBB inverse, that will be WA minus C. That's how you define it. Now, this is, for a minimization problem, it will be less than or equal to 0 if B is an optimal basis for a minimization type standard form problem, okay? That's how you stop. It's, you know, all reduced costs are non-positive, so there's nothing to enter. However, it will have at least one positive component if B is not an optimal basis. In that case, of course, there's at least one reduced cost which is positive. Not less than or equal to 0 means at least one component is positive, in which case you can enter that and get better in the objective function's value. So if you look at this, actually, this is the left-hand side minus right-hand side of dual constraints. See? That's what it is. So whenever R is less than or equal to 0, that means W defined by CBB inverse is actually less than or equal to C, because you've got that. And whenever R is not less than or equal to 0, that means WA is not less than or equal to C, which means at least one dual constraint is violated, okay? So anyway, that's why we use the term dual feasibility actually to mean that the reduced costs are they either have the correct signs or at least one of them has the incorrect sign. All right, so with that, the primal simplex method works in the following way. It tries to, well, it maintains primal feasibility in each iteration, meaning that whatever solution you have on hand, xb defined by b inverse b and xn equal to 0, they satisfy, of course, ax equals b because, when you partition, that's what you get. Also, the non-negativity is always satisfied. Okay? Because if you partition A into B and N, then AX equals B simply gives you BXB plus NXN equals 0. XB is defined by B inverse B, so this will, and XN is 0, so this certainly satisfies the equalities, and xb is always greater than or equal to 0 throughout. We begin with that, and we always maintain that. So this is always satisfied. The dual feasibility is not satisfied at all until the very end. So at the very end, you actually satisfy that. That's why you stop. So we work towards it, towards satisfying dual feasibility. And we never do satisfy that except in the final iteration. And the dual feasibility simply refers to R being less than or equal to 0, which is the same thing as W defined by CBB inverse, satisfying your dual constraints. Okay? That's what dual feasibility stands for, and satisfied only if B is an optimal basis, and otherwise it is never satisfied. Okay? The third condition is the complementary slackness conditions. Which refers to the satisfaction of the complementary slackness conditions at variable times, the left side minus right side of the constraints. So in our case, these are also satisfied or maintained. Let's just write satisfied. Also, this one is satisfied. I think that's a better term. All right. Because if you look at W times AX minus B, you're supposed to have equal to 0 here. That's part of the conditions. And the other part is WA minus C times X must be also equal to 0. Those are the conditions. Now, this one is satisfied because AX is always equal to B, which means this part is 0. For that reason, you obviously satisfy this part. This part is also satisfied. Why is that true? Because if you write this in partitioned form, then what do we get? We get WBCB times, well, let's just write it down, and then WN, sorry, this is not true, WB minus CB, yeah, sorry, and Wn minus Cn, that's what we get, times x, and x is xb xn. So this gives you Wb minus, well, Wb minus Cb is how much? If W is defined by CBB inverse, which is the case we have, that will give you CBB inverse B, which gives you CB, so the first part gives you 0. Okay? The second part gives you whatever it gives you. Could be anything. It gives you just Rn. Okay? Here, XB and Xn is 0 by being non-basic, so the output is 0 plus 0, so it's 0. So everything is satisfied. Complementary slackness conditions are always satisfied. All right, so this is your regular simplex method. It maintains or it satisfies primal feasibility and complementary slackness throughout, and it satisfies dual feasibility at the very end. Now, the dual simplex method for optimality, you still need the three conditions. The three conditions come from the duality theorems, actually. The primal feasibility, you never satisfy it until you get the optimum, so you work towards it. You always satisfy dual feasibility, and you always satisfy complementary slackness. Okay, that's how you go in the dual simplex method. So let me give you the general idea here. This is the regular simplex tableau, except that in the regular simplex tableau we have non-negative right-hand sides, but this time we're not going to have that. The equalities will be still maintained. However, there will be something negative here. Okay? That tells you that some basic variable, whereas it's supposed to be non-negative, it is actually negative. Okay? So we've got, say, B1 bar, BR bar, BM bar, and let's just assume this particular one is negative. There may be more than one. Okay? Change this to BM. I made a mistake here, so that's an M. All right, that's the tableau. The y vectors are the b inverse times the original aj column. Okay, so now dual feasibility satisfied means r is less than or equal to 0 for a minimization problem. And it's greater than or equal to 0 for a maximization problem. Okay? Let's just assume that the problem on hand is a minimization problem. And complementary slackness also satisfied, which is the same thing as I have shown before, as in the primal simplex. Primal feasibility is violated due to BR being less than 0. There could be more than one violation. Okay? So, what you want to do is you want to remove such violations and you want to somehow eventually get to a basis where all of them are satisfied. To remove that, we're going to do pivoting. What you're going to do is you're going to make that particular variable leave the basis because it's negative now. You want to actually make it 0 so it becomes non-basic. And the question is, so you decide on the leaving variable first. The question is, how am I supposed to enter, or which variable am I supposed to enter now to make sure that the dual feasibility at the top is still being satisfied while you do not wish to add any further violations on the right-hand side column. Okay? All right, so you want to make sure that the pivot element you choose is, well, first of all, it must be non-zero. And number 2, it should be negative because once you divide the pivot row by a negative number, this will turn positive. Okay? That's why you want a negative number. So, want to choose a negative pivot element in row R. That's what we want to do. All right. Now, if you have a single negative number here in that row, of course, that's the one to choose. But if you've got many negative numbers, then you need to make sure that you choose the proper one so that the RJs don't turn into an incorrectly signed number. Okay? You want to make sure that they still are less than or equal to 0. So, choose among the negative values in row R, the one which gives Rj cap less than or equal to 0 for every j after pivoting is accomplished. Okay? Once the pivoting is done, you want to have the new Rj's still being less than or equal to 0. All right, it turns out that, well, how does the pivoting work? When you look at the new row R, if you happen to choose, for example, YRK as your pivot element, what will it be? It will be the old row R, then minus RK times, right, the new pivot row. And the new pivot row is 1 over YRK times the old pivot row. So if you look at the jth element here, so for every j going from 1 to n, the new Rj, so we're just looking at a particular element here. The new Rj will be the old row R element, which is Yrj, right? Minus Rk times 1 over Yrk, so 1 over Yrk, times what did I do? This is not correct. This is supposed to be old row R, sorry. This is supposed to be Rj, yeah. Old row R. Rj comes from the old row, and then Rk times 1 over Yrk times Yrj. That's what I need, right? Okay, for every j. So you want to make, you want to have that inequality. Now, if Yrj is positive, well, first of all, if it is 0, if Yrj, well, there are three possibilities here. If Yrj is equal to 0, then this will not affect, so this inequality will be satisfied in that case. Okay, so this case is okay. If Yrj is positive, if it is greater than 0, then you're subtracting from the old value something positive, right? Why? Yrk is less than 0 or 0. Yrk is less than 0 because we picked a negative number. So negative divided by negative, that's positive. There's another positive here. So the whole thing is positive. So you're subtracting something positive from the old value, which means that you still maintain the inequality here. The only case that will cause problems is the case when this is less than 0. Okay? So in that case, if Yrj is less than 0, we require, due to the inequality, that Rj be less than or equal to Rk divided by Yrk times Yrj to be this way. And then if I divide both sides by Yrj, I'm going to end up with Rj over Yrj here, except that Yrj is negative now, so this changes this way. And this goes away. Okay? So you want to pick your pivot element so that these inequalities are maintained or satisfied. Which means that, hence, we choose K so that the ratio of Rk to Yrk is the smallest of Rj over Yrj over those j such that Yrj is negative. Okay, that's the way you should choose. It's like the minimum ratio test of the regular simplex method, except that rather than using the right side and the column to enter, you're using the row to exit and the top row. And if you look at it this way, you know, that's actually the regular simplex method, essentially. Okay? All right, so this is how you pick it. For a maximization problem, you should also work this out. In that case, you'll probably end up with maximum ratio, or I'm not sure now. But typically, to take care of both cases, people invented, let's just look at the absolute value, which works for both cases. So, does it work here? Rj is negative, right? Yrj is negative, so the absolute value, yeah. So this is equivalent to choosing the ratio whose absolute value is, was it the minimum or the maximum? I never remember these things. Let me just check. Yeah, it is the minimum, yeah. So you choose the minimum absolute ratio. This also works for the maximization problem. Okay, you can work it out. So let me give you an example and then we'll finish this up for today. The example I'm going to give you, you might have seen it somewhere else before because I usually use the same example in my undergraduate course as well. So let's see. The example problem has the following. We want to minimize 2x1 plus 3x2 plus 4x3 subject to x1 plus 2x2 plus x3 greater than or equal to 3, 2x1 minus x2 plus 3x3 is greater than or equal to 4. Canonical form, minimization. Okay? Except that we'll change it into a standard form. So, if you look at the standard form, we just subtract surplus variables from both constraints. So the problem becomes so that's the new problem in standard form. If you wanted to solve this using your regular simplex method, you don't have a starting basis, so you need to add two artificial variables and then use phase 1 and then continue to phase 2 if you have a feasible basic solution at the end of phase 1. Rather than doing that, what we're going to do is we're going to multiply both constraints by -1. So this will become minus with a plus and a minus on the right side. And I'm going to use this version beginning with the basic variables x4 and x5, except that they will have the wrong sign. x4 will be -3, x5 will be -4. So this will be the format for which dual simplex method really works. So the initial tableau is this one. These are the initial basic variables. We have 1, 0, 0 here, -1, -2, -2 plus 1, -1, -3, 1, 0, 0, 1, -3, -4. And then at the top we have -2, minus 3, minus 4, 0, 0. And of course, the objective value is also 0. Okay? So, for dual simplex method, well, we have two negative ones. If you choose the most negative, you pick that one as your exiting variable. And then we look at the ratio of R value to the negative number in the exiting row. So minus 2 divided by minus 2, that's the ratio you're looking at, okay, for this particular element. Over here, we look at minus 4 divided by minus 3. This one is the smallest, so we enter that one. And we pivot on this element. When you pivot, we get the following. Okay, this is what we have. Meanwhile, the objective value went up from 0 to 4. Even though we're trying to minimize, we're getting worse in the objective value. Why is that true? Because in the initial solution, you're outside of the feasible region. You are so-called super-optimal. You are more optimal than you ought to be, okay? So you're trying to get back to the feasible region. You took a step. You are closer to the feasible region now, except that, of course, your objective value became worse now, okay? Because, you know, you're trying to get feasible. All right, so at this point, I still have something to exit here, that negative, and I have two ratios, minus 4 divided by minus 5 halves, so let's just write them, minus 4, minus 5 over 2, and minus 1, minus 1 half. Which one is smallest here? X2 is smaller? Okay. So you pivot on that one. And we have a new solution now. Okay, now I have dual feasibility, primal feasibility, complementary slackness always satisfied. So this is the optimal solution. What is the optimal basis? The columns associated with x2 and x1. The x2 column is, where's my? Is it -2, 1 or 2, 1? Which one? Is it this one or is it 2 minus 1? 2 minus 1. The original problem data is the data in the standard form, okay? And what about x1? So 1 and 2. Okay? That's supposed to be the case. And of course, what you see here is the inverse of minus b rather than plus b. Okay? Because I pre-multiplied the entire thing by minus identity at the beginning. For that reason, you have a copy of b inverse here, except that it's multiplied by minus 1. So it's minus b inverse that you see in the last two columns of the tableau.